Welcome to day 9 of the Advent of Code. Today is all about finding numbers that add up to a given target. For part 1, we have a preamble of 5 numbers, and the next number is the sum of 2 of those 5 numbers. In our case, that would be 15 and 25. And note that we can't simply take 20 twice. It must be 2 different numbers. Okay, and then we shift our window by 1 and say 2 of these 5 numbers add up to 62. That would be 15 and 47. And then we shift the window again and say 2 of these 5 numbers should add up to 55. That would be 15 and 40, and so on. And then the first number that doesn't satisfy this criterion is 127. There is no number here that, or no pair of numbers that add up to 127. Okay, so how would we systematically check these 5 numbers for all the pairs? Well, I thought of the following solution. Let us iterate I through the first 4 numbers and let j always be bigger than I. Okay, so for example, when I is 0, we start j with 1 and then iterate to the right. Then we move I1 to the right and iterate the remaining 3 positions. Again, I to the right, the remaining 2 positions. And at the end, there's only one possible combination. Okay, so this way we make sure that we don't swap I and j and get 2 times the same answer, or that I and j are at the same position. Okay, so this is the small example. And here we have a larger input, the real input for the puzzle. And to make experimentation a bit simpler, I define numbers to small, and later numbers will be a function parameter. If we compile the entire program, we got an interesting error for the first time. So now the numbers are very big. This number doesn't fit into an int anymore, so we can't use integer parseInt. Instead, we have to use long parseLong, and then it should work. Okay. Cool. So how would we start? So maybe let's start here with the small numbers, and let's think about the iteration in this concrete case. So how would we do it? We could say I should iterate through the range from 0 inclusive to 4 exclusive, so 4 different numbers. Let's immediately look at the numbers to see that we don't have a off by 1 error. Yeah, 0, 1, 2, 3. These are exactly the numbers that I should iterate through. Okay, and then j should be should start at the increment of I and then go less than 5. Right? Let's see if that works. Yeah, that's looking good. So you can see this is our first one that would correspond to this line in the diagram, and that's our last one that corresponds to this line in the diagram. Okay, so remember that the to index is always exclusive. Okay, cool. Now we can start filtering within the for expression. We can say when, well, what's our target value here? That would be 40. When 40 is the sum of numbers at I and numbers at j, right? So for the first iteration, that would be 35 plus 20. Then we're actually interested in the number. And let's see what happens. We get the indices 2 and 3. So these 2 numbers, and indeed, they sum up to 40. Okay. Yeah, it doesn't really matter if we return the indices or the numbers. What matters is that we return anything at all. And we only need one result. That's why we use first. And in case we don't find any result, then the entire expression will be nil. For example, if we search for a different number, right? Let's say 42, then we get nil. Okay, so that's already looking quite good. Maybe now it's time to abstract this into a function. Let's call it sum pair of numbers and a target value, like this. And then we have to think, well, where do the 4 and the 5 and the 40 come from? Well, the 40 is just the target. And this has to do with the length of the numbers that we, the numbers collection that we pass in, right? So maybe let's say n should be the count of numbers, And then we can say 5 is n and 4 is the decrement of n. Okay, so here's our sum pair. Maybe we can test that and say what is sum pair of, let's copy paste for now, 1, 2, 3, 4, 5. Okay, and 40, and that should still work. Yeah, and in case we don't want to copy paste this from above, we can also say subvec of small from 0 inclusive to 5 exclusive. That should give us the same. Yeah, and maybe one more test. The next number would be 62. So let's say from 1 inclusive to 6 exclusive, and then 62. And then we get indices 1 and 3. That would be 20 and 25. That's not correct. What did I do wrong? 62. Oh, right, because the subvector now, of course, has a relative addressing. So for the complete small vector, that would be 2 and 4, right? 15 and 47, indeed. That's 62. Okay, so that seems to work. Okay, cool. Right, so now let's see if we can find the 127. So let's say, how would we do this now? Let's think about this. So we have to potentially scan through this entire collection and always look at the 5 numbers and the target. But of course, that doesn't work everywhere. For example, here it doesn't work because here are not 5 numbers plus a target, right? So if we just use the range and the count of the collection, then this would be our last index, and that's probably not a good idea. But if we skip 1, 2, 3, 4, 5 to the left, then we have 1, 2, 3, 4, 5 elements to sum up, and we have a target value to compare to. So that's already an important first observation. Okay, so we make a for comprehension again and say we want the range not to the count of numbers. That would be too much. We want to subtract from that, or subtract n. In our case, that would be 5, right? We're still using the small example here. Okay, and then let's say that k is I plus n. Okay, so that would be the end of our subvector and also the target index. So let's compute the end of our window here. That would be subvector of numbers I and k, and the target would be numbers at k. Okay, so for the first run, this would be the subvector and this would be the target. And for the last run, this would be the subvector and this would be the target. That should be correct, hopefully. Okay, and then we have to filter again. Let me do it here. So we have to say we are only interested in those combinations of window and target when not some pairs of window and target, right? When that returns nil, when it doesn't find a pair that sums to the target. Okay. Clojure 4. What did I do wrong? Let's see. Oh, I didn't put any result here in the comprehension. So what do we actually want? Maybe let's put the I for now. Okay, n is of course 5, and some pairs is singular. Okay, then we get the index 9. Let's see, index 9, 5, 6, 7, 8, 9. That would be here. So 1, 2, 3, 4, 5. There's no solution 2 pairs in this sequence that sums to 127. Yeah, that's correct. But it would probably be easier to understand to simply return the target here, right? So we didn't find a value for the target. Okay, cool. So I think we can already abstract this again. We're also only interested in the first number that doesn't match in case there are multiple. I don't think there are, but then you don't have these pesky parents around the 127. And then let's write the function. Let's call it invalid of n and numbers. Then the 5 becomes n, and this 5 becomes n. And the numbers that was previously the global def is now the parameter. Okay, cool. So let's see if we did anything completely stupid. So what would be invalid of 5 and small? That would still be 27. And now let's see if it also works for 25 and large, because that's the real input. Yeah, that works. That's the correct number that was accepted by the website. Cool. So that's part 1. This is the first number in the sequence that can't be built by adding 2 numbers 5 places in front. Okay, cool. So the part 2 says, well, now that we found this number, are there or is there a sequence of numbers in front that does sum up, so more than 2 pairs potentially, or definitely. And in this case, that would be 15 plus 25 plus 47 plus 40. And we could, again, compute all the possible combinations. So start with this range, then this range, and so on, up until here. And if we didn't find it, let's compute all the ranges starting here. And if we didn't find it there, all the ranges starting here, and that we will find it. But that's a bit wasteful, and we can use the fact that there are no negative numbers here to make the solution much faster. So I thought, let's start with an empty range that is obviously too small, then add 35 to the range, then we have 35, that's still too small, so let's add 20 in, then we have 55, that's still too small, add 15, then we have 70, add 25, then we have 95, add 47, and now 142 is too big, so it doesn't make sense to put even more numbers into the sequence, at least for now. So let's start removing from the left. So we remove the 35, then we are too small again, so then we can add the 40, then we're too big again, then we can remove the 20, and then we found our match. Right? So we can simply always look at the sum so far in the sequence, and we can keep track of that. And if it's too small, we add an element to the right, and if it's too big, we remove an element from the left. That should be quite an efficient algorithm. Okay, so how would we do it? Again, maybe with a concrete example. So I starts at 0 inclusive, k starts at 0 exclusive. So you really need to get used to these half-open ranges, beginning inclusive and exclusive. And the sum so far would be 0, but I did another little interesting optimization and said, well, let's start with the, well, in our case, that would be 127. Let's not make it more complicated than it needs to be. Okay, so and then I say up until here the numbers will be negative, so I have to grow. Here the number will be positive, so I have to shrink, and here the number will be exactly 0. I just save all those comparisons with 127. I can simply look at the sign of the number. Okay, cool. So let's use our cont that I haven't shown you yet. That's just to make multiple if-else chains more readable and not as indented. Okay, so we can say if s is negative, then we want to recur and say the new value of I should be the old value of I, but k should increment by 1 in the next recursion. And our sum must include also now the numbers at k, right? So the number that previously wasn't in the range is now added to the range. Okay, if it's positive, what do we have to do? We have to recur. I is incremented by 1, k stays the same, and then the sum shrinks by the numbers of I. Previously it was in the range, and now we remove it from the range. Okay, and here you can say true or any condition that is truthy. So you can write else or default, and I like to write otherwise. I think I read that in some Clojure box sometime. It just reads nicely. Okay, what do we want to do instead? So we can simply build a subvector of the numbers from I to k. And let's see if that gives us, oh, that's not inc, which you write, but the increment. Okay, and then we get indeed 15, 25, 47, 40. That's exactly the result we were looking for. Okay, and then the problem statement asks us to find the smallest number and the biggest number and then add them up. Of course, I could do it programmatically, but maybe let's just sort. Let's see the result, and then we can add 15 and 47 in our head, right? That's not too hard. Okay, so I think it's time to abstract now. So let's call it sorted summons of n and numbers. And then, of course, the 127, we have to look for it. That would be our invalid function from before. Great. And the rest should still be fine. Yeah, let's see if that works for 5 and small. Yeah, that's the vector that we just saw. And does it work for 25 and large? Yeah. And then those numbers are a bit bigger. So that would be this one and this one. Yeah, and that was the number that was accepted by the website. Okay, cool. So I think this was quite an interesting problem. So I like to think about this optimization. I didn't even try the brute force. I immediately thought, I don't want to waste precious CPU time. Yeah, I'm not even sure if I learned this algorithm at university or where I know it from. I didn't think of it myself, I'm pretty sure. Okay, and yeah, so today we saw lots of these for comprehensions. They're quite useful. They are still lazy syntactic sugar for all those maps and filters, if you will, but sometimes they lead to very readable, compact code. And a perfect example that programming is not about writing code down, I think, are diagrams like these. So whenever you're stuck writing your for loops in imperative languages and you don't really know where should I start, where should I stop, draw out these kinds of diagrams and make it clear to yourself with a concrete example, and then writing the abstract code becomes a lot simpler. Okay, otherwise you run the risk of running into off-by-one errors or index out of bounds exceptions. So this was a lot of preparatory work for me to make it clear to you. Okay, cool. Yeah, and you probably see in the thumbnail that I replaced this with true because it doesn't really matter what we return here. Anything that is handled as truthy will be okay. Okay, and of course the subvector function is quite nice because it gives you a subvector view into the original vector in constant time. So very fast, you don't have to copy any elements. I didn't mention that. And yeah, in case integer parseInt doesn't work for you, you can use parseLong. Oh, that's a Java function that I can't do it here with the inline help. Okay, cool. So I'm pretty sure you solved these problems in a different way, maybe even this probably, and the first one, I don't know. If you solved it differently, let me know, and let me especially know if you find these kind of diagrams helpful. Then I will include more of those in future videos.